Hello everyone, this is Doug, and in this video we're going to talk about the Aldol reaction, also known as the Aldol condensation, so aka Aldol condensation. And it's called a condensation because you're going to combine two molecules and you're going to make water. So condensations always have water as a product. And condensations combine two organic molecules. Combine two organic molecules. So the reason we're talking about this now is because the aldol condensation has everything to do with the acidity of those alpha hydrogens. And that's kind of been the theme of this chapter and the theme of these series of lectures is that reactivity at the alpha carbon of a carbonyl. So let's take a closer look at exactly what the aldol condensation looks like. So what you're going to see here, right, is that you're going to find that all of these aldol reactions, all these aldol condensations involve two aldehydes and ketones, or at least a mixture of the two of them. Right, it could be or a mix of each. Right, in this case, I have two aldehydes. You'll also need some sort of catalyst that's going to be a base. This can just be kind of almost any base. It's typically a strong base, like hydroxide or something. So I could have, for example, put in NaOH as my base in this case, and you just need a catalytic amount. And then the products that you're going to make are going to be either a beta hydroxycarbonyl, right? So beta hydroxycarbonyl, and this just goes off of your right alpha, beta, gamma, etc. Right? How many are away? And then beta, you have a hydroxyl group, right? 2 carbons away from a carbonyl. So you're going to get some sort of beta hydroxycarbonyl. And we'll talk more about this. I'll point this out when we do mechanism stuff more, but this is what's called the Aldol product. And it's called the Aldol product because originally these were aldehyde. You have an aldehyde and a ketone, or sorry, an aldehyde and an alcohol in the same molecule, right? You have an aldehyde and an alcohol, which are the 2 functional groups in that molecule. Now, like I was saying before over there in green here, right, these can be ketones also. So technically there are also ketols, but no one ever refers to them as ketols, or people rarely refer to them as ketols. People just call them the aldol. This is the aldol reaction that you form an aldol product. There's nothing called the ketol reaction. It's just called, everything's called the aldol. And so you could get this aldol product, or you could get this other product if you have heat, or if you make an extended conjugated system. And I'll talk to you more about that in just a second here. But this other thing it will make is an alpha-beta unsaturated system, which we're already familiar with. Right? We talked about conjugate additions and everything where we form these alpha-beta unsaturated systems. So alpha, beta. Right? You have your alpha-beta unsaturated system. Alpha-beta unsaturated system. Right, because you have an unsaturation, you have an alkene between the alpha and beta. It could be an alkyne, for example. And this is what we call the condensation product. Condensation product. Because what happens between the aldol and the condensation product is that you lose water. You've lost H2O. You're actually down a hydrogen and an O and another hydrogen. You're down water. And what I was saying before is like, so you need heat in order to do this last step. So you need heat, comma, or the alkene needs to connect 2 pi systems. If that alkene formed here, right, so the alkene right here, if that's going to connect 2 pi systems, this is just, you're almost always going to form the condensation product. You won't stop at the aldol, it'll just go all the way. This is an example right here where I'm not connecting 2 pi systems. There's no pi system here. No pi system. So this is not an example where this would happen, just automatically go to the condensation product. You would have to stop at the aldol unless you had heat. But let's look at the mechanism so we have a little better understanding of how we got from point A to point B. So like I said, we're going to involve, I'm just going to use the same reaction that we had in the previous slides. The mechanism basically has 3 to 4 steps, depending on if you go, which product you're making, right? The first step is that your base is going to remove one of those alpha hydrogens. You're going to form an enolate. That enolate is then going to attack the other carbonyl. And then that alkoxide you just formed is going to get protonated by a solvent. And that, you may stop at the aldol at that point. If you continue on to the condensation product, then you're going to have a 4th step, which is that you're going to regenerate your base. Or sorry, you've had a regenerated base, and it's going to attack an alpha hydrogen to basically do a type of elimination, technically a E1CB conjugate base elimination. So let's take a look at what that actually looks like here. If I look at my molecules, right, both of them have alpha hydrogens. Here's an alpha carbon, it's a beta carbon. And so I'm just going to take the alpha hydrogens off of the one on the left, just to, because I have to pick something. And I'm going to draw out my reagents here, right? I got a sodium plus, I've got OH minus, I've got water, and I've got THF. I'll just draw this up here since it's just a solvent. And so what I'm going to do, like I said in the first step, is that my base is going to pluck off one of these alpha hydrogens. And now this step here, right, this base is not strong enough to fully deprotonate the alpha hydrogen, right? It's not like LDA or some negative nitrogen base. So this is a pretty slow step and not a great equilibrium. But the idea here is that as soon as you have, right, your enolate, it's a nucleophile. And I'll draw the resonance structure here for you. Right, the whole reason why these are relatively acidic hydrogens. Right, what's important to note is that now this enolate is a nucleophile. So the idea is that it can go and attack the second carbonyl, right? So let me redraw that other aldehyde over here. Whoop, that whole thing over by accident. And if I look at that other carbonyl, right, I know I have a dipole at that carbonyl. And so I'm going to have my enolates attack the other carbonyl, right? The negative on that carbon is attracted to the positive on the carbonyl carbon. The weak pi bonds kick up onto the oxygen. And I'm going to make a new product, right? I've just made a new carbon-carbon bond here. And what I'm going to do is I'm going to, oh, this should be an H over here, sorry. What I'm going to do is I'm going to keep track of my carbons here using just like an ABC 1, 2, 3 type of deal so that I can keep track of everything. Let me finish drawing this aldehyde here. So if I go back to this, and let's say I call this carbon 1, 2, and 3. I'm going to call this A, B, and C just to keep track of things, right? 1, 2, 3, A, B, C. So now when I look over at my molecule, right, this is carbon 1, carbon 2, carbon 3. I'm going to have carbon 2 attack carbon 1. Let me erase that. So now this is going to be right here. Now we have an O minus. And these are carbons A, B, and C. Right, so I just made this new carbon-carbon bond between 2 and A, that new sucker right there, right? That's my new piece. Now, what we have at this step, right, like we said, we've got water hanging around. We either just have water because we added it, or we made it when we did that first step where my hydroxide took off the alpha hydrogen. And this is that third step that I was saying that your alkoxide here is just going to deprotonate a solvent molecule. It could be water, it could be ethanol, it could be whatever product solvent is around. And that's going to give us our condensation product. And I should say that all of these steps are reversible. All right, so here is our, sorry, not our condensation product, our aldol product. Now, in this set of reagents, I don't see any heat shown. So I would just stop here. If you don't see that something's warmed up and it's not going to connect to pi systems, that alkene, that next step is not going to form a bridge between the two pi systems, then just stop here. But let's just say that we do, right? So I'm going to add in here, slash, I'll say 50 degrees Celsius, right? Something to indicate that something's warm. So if it's warm, now what I'm going to do is the next step, this fourth step here, where I still have an alpha hydrogen here, right? That's still a relatively acidic alpha hydrogen. Let me draw that a little bit better. Right, this is an alpha hydrogen. And I just made in that previous step, right, where I protonated that oxygen to make the OH, I just remade my hydroxide. And so my hydroxide can, again, and this is not the best equilibrium, but it could take off one of these alpha hydrogens so that I can form my new enolate. So now I've got a negative charge. I'm not going to draw the resonance structure because I'm running out of room, but right, there'd be a resonance contributor for that enolate. Just move it into the carbonyl. Let's pretend it's here. Now this is the step, right, that's really weird, why you need either heat or you need some sort of other thermodynamic drive like connecting to pi systems. But what we're going to see here is that this is going to do something weird. These electrons are going to drop down, and we're actually going to kick out OH as a leaving group. And that should seem really weird because we've said so many times that alcohols are not good leaving groups. They're really poor leaving groups. That's the whole reason why we turn them into those sulfonate esters, right? Like the mesylate or tosylate, triflate, or why we turn them into chlorine using SOCl2, or we turn them into bromine using PBr3, something, because they're just terrible leaving groups, right? So this should seem like an awkward step to you. This is not super favorable. But again, this needs heat. But that's what allows us to form our product, right? To form this condensation product. So the condensation product. And again, you'll notice that we reformed hydroxide. So we've remade our catalyst, and which is why we don't need stoichiometric amounts of hydroxide. We just need a little bit of base because it's going to get regenerated. So this is kind of an involved mechanism, but let's see what this looks like, right? If I just want to figure out what the answer is without going through a whole mechanism, what are some tricks so we can quickly get there? Now, if you take a look at these, right, remember that, so it's the same reaction. I just kind of want to show you how we can get from one place to another. One of the things that we had to do, right, was that we had to remove 2 alpha hydrogens. So if you go back and you look at that previous mechanism, right, we removed 2 alpha hydrogens from 1 carbon. We need to remove 2 alpha hydrogens from a carbon. Now, in this case, either of these 2 molecules should be fine, right? Here's an alpha carbon, here's an alpha carbon. They both have 2 alpha hydrogens on them, so again, I'm just going to pick one of them here. Let's say this is the one we're talking about. And the other thing that you may have noticed, right, is that one of the other carbonyl lost an oxygen. So we need to lose an oxygen from the other molecule. Let me erase that. From that other molecule. Which means that I'm going to lose the oxygen from this guy. Right? And in fact, that's what we're going to see, that carbonyl is going to be gone, and you're just going to double bond there. Right? And remember, I called this carbon 1, let's see here. I called this carbon 1, 2, 3, and I call this carbon A, B, C. So what I'm going to do is I'm going to take my carbon here. Here's my starting molecule, and I call this 1, 2, and 3, right? We just said that I'm going to have those 2 alpha hydrogens that right there are carbon 2. That's now going to be double bonded. Whoops, excuse me. that's now going to be double bonded to the other molecule right at carbon A there. So that's going to be a double bond, and there's A. So where this is A, B, C, right? Because A was the purple carbon here that we said we lost the O from. And that's the product that you're going to get. Now, you'd also expect to get the other easy isomer, right? So, and we would expect to get this. It would just be a smaller amount, probably. So you expect to get both of these, but you'll notice that this is that answer, right? I was able to get to that answer pretty quickly. I removed 2 alpha hydrogens from one, removed the oxygen from the other, stuck those 2 parts together. That's what I did. So let's look at some other examples. So here's a whole bunch of other simple aldols. A simple aldol just means you are connecting 2 of the same piece, right? So a simple aldol just means that you have 2 of the same carbonyl compounds. The same ones, right? You'll notice these are the same, these are both propanol, they're the same molecule. And so if you see a reaction like this, right, you'll see just, in this case, a ketone, and then you'll see some sort of strong base, and then nothing else. That's your cue that this is an aldol, right? If you just see a carbonyl, you just see a strong base, that's it. Then you're going to want to think aldol. So I'm going to draw a second equivalent of this. Whoops. I'm going to draw a second equivalent of this so that I can see what pieces I'm going to connect. So I'm going to have 1 and 2. Now I'm going to take 2 alpha hydrogens from one of them, take those 2. Those are the only places where I have alpha hydrogens. And I'm going to take the oxygen off of the other one, and I know that that's where I'm going to connect the 2 together. And so first I'm just going to draw the aldol product where I don't have the alkene. OH, and then the phenyl. Right, so here would be the connection, the connecting pieces, right, where if I number these, let's call that carbon 1 and 2, and let's call this A and B, right? So now I have 1 and 2, and I have A and B, and then the phenols. All right, so I've made that new bond. Now this is a good example here, right, where if I look at this, it looks cold to me. Looks cold, right? This might be like room temperature or something. I don't see a temperature shown, so I'm just going to assume room temperature, which is not enough normally to get that last step with that weird elimination to go. But what we want to look at here, this is a good example of one that has a conjugated system, right? So hopefully you have that drawn. I'm going to kind of mess it up here. What I meant by that, this is a good example to show you, is that right here I have a conjugated system, right? There's my conjugation. I have a pi system right there, and I have a pi system right here. Now, if I was able to get them to connect, that would be a lot more stable, right? To have a larger conjugated pi system. But right now I can't, because 1 and B are both sp3 hybridized, and so one pi system is not talking to the other pi system. However, if I did have the alpha beta unsaturated system, so I had this. Now if you take a look at this, right, and you go ahead and draw it before I start messing it up here, right? Again, I have a pi system, but now because there's an alkene here, now they're connected, now they're talking, right? So you've extended this pi system. That's what I mean by you either need heat or you need to have, your alkene needs to be able to extend the pi system, then you're gonna go to the condensation product. And this is exactly that example, right? So this would be your major product over here. You'd get the condensation product. Right, that would be your major product. Even though there is no heat, even though it was cold, if you form that really stable extended conjugated system, then you're going to form the condensation product. You're just going to. Let's look at this example over here, the next one. Same thing, I just see a base, I see a ketone here. So I'm going to go ahead, I'm going to draw out my second equivalent of this. And I'm going to do the same thing, I'm going to find my alpha hydrogens. So here I have an alpha spot. Let me erase that. Here I have an alpha spot. Here I have an alpha spot. But you'll notice here, right, that I only have one alpha hydrogen on the left, but I have 3 on the right. And I need at least 2 alpha hydrogens in order to do this. So I'm going to choose the right-hand side, right? You're not going to do an aldol reaction where you only have 1 alpha hydrogen because it's going to unravel. It's not going to be a stable product. And then, so that means I'm going to attack the O from this other one. And then you just connect the pieces together. So I've got this isopropyl methyl ketone thing. It's now going to be single bonded to this, and it's got an isopropyl piece on it. So that would be my product for that, right? Again, notice that here it's cold. It flat out says it's cold. So then you just stop then at the aldol product. We're not going to continue on to the condensation product. You're not going to get that alpha beta unsaturated system. You're going to stay at the beta hydroxy. Versus this one right below it here, right? This is warm. Right? People did add heat to it. It has been warmed up. So instead of drawing the aldol product, I'm going to draw the condensation product. Right, so I know that I did that extra E1CV step. I did that extra step. So these are all quote unquote simple aldols where you're mixing 2 of the same carbonyl together. We also have what's called mixed aldols, and let me show you those. These would be considered mixed aldol reactions, right? So they're mixed because they're 2 different carbonyl compounds. Right, they're 2 different compounds here, right? I've drawn them both out here. And what you're going to do with these mixed ones is you need to find your alpha carbon that has the 2 hydrogens, right? Because if I look at these compounds, yes, I've got an alpha carbon, and an alpha carbon, but only one of them actually has alpha hydrogens, right? Only this one has alpha hydrogens. So I know that that's what I'm taking the 2 hydrogens from, which means it must be attacking this carbonyl. And so I put those 2 together. Right, there weren't alpha hydrogens at either of those other spots. So there's really only one way I could really combine these. And this is another one where I'm going to stop at the aldol product because I don't see any heat. So I'm just going to stay there at the aldol product, keep the beta hydroxy. I don't see any heat, nor would the alkene start connecting 2 different pi systems. If I look at the second one, the same deal. Look for my alpha spots. So alpha, alpha, alpha. Same thing though, right? I only have one place where there's 2 alpha hydrogens. My students might recognize these. Maybe. This is actually the first lab experiment you all did. It was the solventless aldol reaction. We called it a melting point study. But you mix these 2 things together, right? And you just straight up added hydroxide. There's no solvent really at all. And what was nice is that there's only one set of alpha hydrogens, so you're able to make a pretty clean product, relatively clean product. And in this case, you do connect 2 pi systems. So it just automatically went to your product. So I'll have this spot right here. It's now double bonded to that dimethoxybenzaldehyde to form that as your major product. And again, that would be a condensation product. And the reason why it went, even though we didn't add any heat to it, again, was that you had a pi system, and now this alkene connected the 2 of them. So it just went all the way. And I'll erase that, or you can go back in the video and draw that without all that red drawn on it. And lastly, I'm going to look at this one down here. I have an alpha carbon. These are all my alpha carbons. And now if you take a look at this, right, the problem is that at all three of those, they all have 2 alpha hydrogens. So which one then should I take the 2 hydrogens from, right? Let's call this carbon 1, 2, 3, and 4. Let's call this A, B, and C. This is a terrible example of a mixed aldol reaction because there's so many combinations I could get, right? Like let's say I took the alpha hydrogens from carbon number 1. So let's say I took the alpha hydrogens from carbon number 1 and I had to attack the aldehyde, right? I had to attack carbon A. Then I'd get something that looks like this, right? Where this is carbon 1, 2, 3, 4. This is A, B, C. But there's no reason why the hydrogens from carbon 1 were removed. It could have been the hydrogens from carbon 2 that ended up getting deprotonated. And then we'd attack the aldehyde carbonyl, right? So we could have done 1, 2, 3, 4, attacking A. Or, maybe I took 2 hydrogens from B, carbon B, on that aldehyde. Maybe that's what happened. And maybe that ended up attacking that 2-pentanone or 2-butanone. Right? And so we got something like this instead. So I had B attack 2. Right? I could have mixed it up like that. Or I mean, and this is true for all aldols, but they could have attacked themselves, right? I could have had my ketone attack another one of the ketones. So I could have had the ketone attack itself, where I had 1, 2, 3, 4 attack 1, 2, 3, 4. I did a self-condensation. Or, I mean, I could just keep on going and going. Right? There's lots more. I didn't even show all the stereoisomers, right? I didn't even talk about the E and Z possibilities here, but there's so many ways, right? I could have the aldehyde attack itself. I could have the ketone at 3 attack itself. There's just so many different possibilities. This would be a terrible example. This is a terrible mixed aldol. If you are ever going to do a mixed aldol, you want to make sure that you basically just have like one molecule that has the alpha hydrogens so that you don't get these crazy mixtures, so that you take off the hydrogens from that one molecule and then it attacks a different carbonyl, ideally. But anyways, I hope you have a better idea now of what the aldol reaction is. Really the key is that, again, you pluck off those alpha hydrogens, you make an enolate, and then you have that enolate, that new nucleophile, just go attack something electrophilic. And in this case, it's just another carbonyl. And that's called the aldol reaction. So do some practice. Let me know if you have any questions. Happy studying.